Now, if you're following along in the handout, you're right to here, which was where we found an estimate for the amount of escaped air. It sucked because the air was too big. Remember, that estimate was also an estimate for the area under the rate graph. Now, how can we find a better estimate so with a smaller error? Well, if you notice, I don't know if you notice this or not, but for each of the estimates, the upper bound and the lower bound, in the first part, we only used 1 point of the whole graph, right? And this graph has an infinite number of points, so we certainly can do better. And in round 2 of this, what we're going to try to do is use 3 points for the upper bound, 3 points for the lower bound, and just see what happens to the error when we do this. So I'm going to switch over to the little whiteboard, and we'll try to draw a little bit and just see what we can do. Now, what I want to do is, instead of going over the whole 3 seconds, I'm just going to go the first second interval, the second interval, and the third second interval, and just do each. So what I want to do is, when I'm calculating the upper bound, I'm going to look at, I guess I need some points here. See, I still know the top was 8. This point has height 4. This point has height 2. This point is height 1. There, that'll help some. Now, if I want to find an upper bound for the amount of escaped air, but just during the first second, I can still use the 8, right? So that's still going to be 8. That's still going to be cubic feet per second. But now, I'm only doing it for that first second. Seconds still cancel, and I get 8 cubic feet. Now, what is that 8 cubic feet? 8 cubic feet is guaranteed to be bigger than the amount of escaped air during that first second. Now, by the way, if you notice, that's also the area of this rectangle, which you can see is also bigger than the area under the rate graph. Now, let's look at the second interval. In other words, the time interval that starts at t equals 1 second and ends at t equals 2 seconds. I'm looking for an upper bound, so in the time interval between t equals 1 and t equals 2, I'm looking for the fastest the error came out. Well, that's not 8, that's now 4. So if I'm looking for an upper bound here, I'm going to take my 4 and cubic feet per second. I'm going to multiply by the 1 second I'm focusing on. The seconds cancel. I get 4 cubic feet. Now, what's 4 cubic feet? 4 cubic feet is an amount of air that's guaranteed to be bigger than the amount of air that came out between the 1 second mark and the 2 second mark. But by the way, because this was 4 times 1, here's the 4. Guess I want that in orange. Here's the 4. Here's the 1. And when you multiply two numbers together in a math class, that's always the area of something. In this case, it's the area of this. So the first computation I did was that area. The second computation I did this area. And notice, even though I'm finding a better upper bound, it's still an upper bound for the area under the rate graph. Now let's do the third second interval. The third second interval, let's see here. I now look between t equals 2 and t equals 3. I'm looking for the fastest it ever went in that time interval. Well, that's not 8 and it's not 4, it's now 2. Right. So what I want is the fastest in that time interval is going to be 2 cubic feet per second. And this is going to be times the 1 second. The seconds cancel, and I'm going to get 2 cubic feet. Like that. Notice, by the way, the 2 times 1 is always the area of a rectangle. Which rectangle? The rectangle that was 2 units high and 1 unit wide. And this is the area that we just calculated. So the first area calculated was bigger than the corresponding area under the rate graph. The second calculation gave me an area that was bigger than the corresponding part of that rate graph, etc. If I want a total upper bound, what I'm going to get is 8 plus 4 plus 2. That's 14 cubic feet. Remember, my first upper bound was 24. We were guaranteed that 24 was too big. Now I'm guaranteeing that 14 is too big. that's actually a much better estimate. It must have gotten much closer to the actual value. So an upper bound for the amount of escaped air during that time interval is 14 cubic feet. But we were after for the same kind of thing we had before, where we wanted an estimate and a plus or minus error. Well, the problem with that, in order to do that, I now need a lower bound. So we're going to do this exact same calculation. This is painfully slow, because we're basically bootstrapping ourselves from nowhere. Here we go. Now we have to find a lower bound. Hopefully a better lower bound than we got the first time. So we're writing lower bound like this. Lower bound. We have the same graph. We are focusing over a 3-second time interval. So there's 1, there's 2. I know how high these dots are. We calculated these before. This is 8, this is 4, this is 2, this is 1. Right. Now what do I want? I want to calculate an upper bound for the amount of escaped air. I'm going to do it the same exact way. I'll go a little bit faster this time. Hopefully my thing will start. There we go. Clicked in. All right. So what I want to do is just look at the first time interval from 0 to 1 second, and now I want to pick the slowest the air went. Well, that is in this time interval right here. So I'm going to take 4 cubic feet per second, because that's the how high the dot is on the rate graph at that point. And now I multiply by 1 second. Now why 1 second? Because I'm only looking at that first second time interval, and I get 4 cubic feet. Now what is 4 cubic feet? 4 cubic feet is guaranteed a lower bound for the amount of escaped air, and you can see that that same exact 4 cubic feet is area under the rate graph at that point. Let's look at the second time interval, just from t equals 1 to t equals 2. I'm now looking for the slowest the rate ever went. Well, the rate is going down here, so the slowest the rate ever went is the height of that dot, which is 2. And so what we're going to do is multiply that slowest rate, 2 cubic feet, times 1 second. Didn't say that right, here we go. 1 seconds cancel, and I get 2 cubic feet. Yay, what's that 2 cubic feet? That's guaranteed lower than the amount of escaped air between t equals 1 and t equals 2. But whenever you see a product in a math class, that's going to be an area. What area is that? It's the area of this rectangle, whose height is 2 and whose width is 1. And you notice that not only is 2 a lower bound for the amount of escaped air, but that same 2 is a lower bound for the amount of area under the rate graph during that time. Finally, I'm going to calculate a lower bound for the amount of escaped air from t equals 2 to t equals 3. Well, the slowest it ever was going was 1 cubic foot per second. So I take my 1 cubic foot per second, and I multiply by my 1 second, because we're only looking at that 1 second interval over here. The seconds cancel. I get 1 cubic foot. What does that 1 cubic foot represent graphically? Well, this is 1 times 1. Well, which 1 times 1? Well, this height, 1, because that was in the cubic feet per second, times this 1 second. Now, when you multiply two things together in a math class, it's always the area of a rectangle. And I'm going to get that. And we find out that this 1 cubic foot is not only a lower bound for the amount of escaped air during that time period, it's also an area that's lower than the area under the rate graph at this time. Now, what are we going to get for a lower bound here? I'm going to put LB for a lower bound. I might want to put more stuff over here. I'm going to get 4 plus 2 plus 1. That's 7. 7 cubic feet per second. Now, so we can see it. Yay. Now what I want over here is I want to find my total guess. What we found in the first round, the first part of the second round, was that 14 was our new upper bound, and 7 was our new lower bound. The average of 7 and 14 is 10.5. So my best guess right here is going to be 10.5 cubic feet plus or minus the error. Well, the error the actual value has to either be between 7 and 10.5 or 10.5 and 14. In either case, the actual error is going to be less than that distance. So it's going to be plus or minus 3.5. Now, one more thing to notice, because I'll have you be doing something like this. In the first round, the plus or minus error was 10.5. In the second round, the plus or minus error was 3.5, which is a lot smaller. But we can actually be more precise about this. In the first round, we only used one rectangle, and we got an error of 10.5. In the second round, we did 3 times as much work, and the error, the plus or minus error, got cut by a factor of 3. In other words, if I was willing to draw 100 rectangles, I would expect the error to go down by a factor of 100. It's very fair that way. You do 1,000 times more work, the error gets cut down by a factor of 1,000, etc. All right, on to your turn.